So yeah, my name is Martin. Welcome to the first workshop of the day. Finally, we can start building something together. So I work for HydraDX and Basilisk. So as you can see, the title of this workshop is implementing different types of AMMs in Substrate, which focus on these little things which can surprise you when you try to create and develop AMM in Substrate. I chose this topic because for Basilisk we developed several AMMs. Some of them are live, some of them will coming up. And also for Hydra we implemented a new unique AMM, which is called Omnipool. So what I want, my goal for today is to give you an idea what it takes to implement an AMM in a Substrate, as a Substrate pallet, and with the focus with these little things. You know, we won't be talking about what's the pallet because that's a little bit more basic, so we want to actually create something. And I was thinking how to do this because, you know, when you have a workshop, you expect some hands-on experience, but we have limited time, and doing something and writing something in Rust and Substrate takes a long time, right? So instead of writing the code itself, I will already prepare the code. So we will be looking at the code. We'll go line by line, but we won't be writing it because we would be just fighting the compiler and waiting for the build to complete, and we would not achieve anything. So I didn't really time it, so I don't know how long it takes. So if there is some time like left at the end, we can discuss and even hack something together if there is enough time. So agenda for today will be like, I will also do the brief introduction what is AMM. Even I think most of you, not all of you, knows what it is and how it works, but I think it's better to get everybody on the same page and then build on the top of it, so we can see like what are the questions and how we want to resolve them and create the AMM. So then we will also mention different types, like there are many different types, we mentioned some of them and what are the differences, and then we will start actually designing the palette, right? So based on what we talk about what is AMM, we will have some questions and then we will try to answer like how can we do this in Substrate. Then we will look at the mathematical model because I think you already know that the most important part of AMM is the actual mathematical model, which can be tricky to come up with, but we won't be actually creating anything new. We just take the existing AMM mathematical model, we will try to do that. But we will focus on these things in there which can cause problems, right? So then we will also briefly touch on testing and benchmarking, because as you will see, to implement the AMM is not really that hard, right? If you know Substrate, you know Rust, and you have given the spec how to do that, it's not really that hard. But the tricky part is the proof that is right, that is correct, right? And that the testing will help you with that. And there can be testing strategies that can help you to prove that your implementation is correct. And then in the end, like I said, we can have some question and answers, right? So a little disclaimer, right? I'm not expert on AMMs. I don't claim to be, right? Hell, I didn't even know what is AMM 3 years ago. And so everything what will be said and shown today is mine approach and our team's approach to implementing AMMs. Can be done, I'm sure, in many different other ways. And if you disagree or if you have other opinions, just raise your hand, we can discuss it, we can fight if you want. And yeah, so let's start, right? So what is an AMM? So question I have, who doesn't know here what is an AMM? Or I expected that. Everybody knows what is an AMM. But I think, like I said, better be on the same page, and there might be a little alone somewhere among you who doesn't want to admit, doesn't know what it is. So AMM, automated market maker. So to understand it better, let's split it into two parts, right? Market maker and automated. So let's first explain what is the market maker, right? So market making, how can I say this? Market making is a process of providing liquidity to an exchange, right? And those who provide the liquidity, those entities can be called market makers, right? So example, in a typical centralized exchange, right, you want to swap your one asset for another. So you express your intention, right, and to an exchange that you want to swap asset A for asset B. So this exchange keeps the order book, right, of all intentions of the users and tries using some order matching algorithm tries to, match this intention and settle them. So, but in some scenarios there might not be enough counterparts to this, so you won't get your asset B, right? So for these purposes, there are these parties and entities which constantly buy and sell various assets at various prices. So, and that what they create these market makers, right? So now we append this automated in front, and what are the differences, right? So now we are in the decentralized exchange. So instead of you dealing with these market makers directly, you deal with this pink stuff here, right? So this pink stuff here is the liquidity pool, right? So on the one side, we have the liquidity providers. On the other side, we have the traders. The providers deposit the token to the pool, right? They provide some liquidity to the pool, and they don't need to worry about anything else, right? So on the other side, we have the traders. This is you who comes and wants to swap one asset for another one. And the responsibility of this pink stuff here, right, the liquidity pool, is to automatically calculate the token quantities for the transactions, right? So the exchange ratios is automatically determined by the current state of the pool, by the mathematical formulas, and it will calculate how much you should receive from the pool if you want to trade an asset. So now we might have a question like, what is the benefit, right? What makes it interesting for a liquidity provider to actually provide liquidity, right? So yeah, simple answer is that you expect some rewards, right? So how this is achieved in the liquidity pool, in this automatic AMM, right? The simple answer again, we have some fees, right? So imagine you have a research guy, right, named Colin. We have a research guy, his name is Colin. So everybody should have a Colin in his team, which comes up with this mathematical model, and he also incorporates all the fees, like how you should calculate everything, and also includes fees, right? So then these fees are paid by the traders, right? Every transaction pays the fee. The fee stays in the pool, and all the fees accrued in the pool are then distributed among all the LPs which provided to the pool based on the share of the pool, right? So also this comes with all the risks, right? So AMM, the risk is the impermanent loss, but I won't go into that. So now different types of AMMs, right? We have many different types of AMMs, which has different properties, different invariants which they follow, the curve they follow. So we have the constant product implemented by Uniswap or Basilisk. We have implemented the XYK on Basilisk. Then we have the constant sum, market making, and a constant function. This is the stable swap or curve, which is also implemented on Basilisk as well. Then we have the constant meme, done by Balancer or our LBP, Liquidity Bootstrapping Protocol. And then there is this new kid on the block, which I already mentioned, and that's the Omnipool. The differences are that, for example, in this XYK, the first one, you have two assets in the pool. Here, you can support multi-assets pool in stable swap. Usually, you have two assets here as well, but in Omnipool, it's all assets in one giant pool. So, what are the differences now, right? So the difference is like each of the AMM follows like different invariants. So for the first one, where you have this invariant which must hold and that's the product, right, must equals to some constant. Then you have this table stuff, which is a little bit more complicated, right, because it combines the best of these two. Then you have this one, which, you know, if you are a developer, you look at these and you already have some concerns because there is this power to something which doesn't look nice, right? This rational number. Then you have constant sum, which is very easy. Nobody uses it as far as I know. And then omnipool has something quite complicated, so I would say you don't really want to know. If you want to know, then you can talk to us after the presentation, and we can discuss how it works internally. So looking at this, you might already have some concerns, right? So what do you think is the ultimate concern you always have when you have an AMM running on your chain, right? Exploitation, right? You implemented your AMM, you are confident it works, but you have something in your mind that's back, you know, telling you that, what it gets exploited, right? So let's have a look, like the famous, well, not famous, several hacks or several root causes which can be the problem and can get exploited, right? So what can be some problems which you might encounter in AMMs, right? So incorrect calculation, right? That means you have your formulas, you have your spec given by Colin, and there are some things to calculate, and you do some mistakes here and there, and it might look okay in your test, and we will see some examples where it was not obvious during our testing, but it was found later that there was an incorrect calculation. Then logic problem, yeah, typical, right? So example, you implemented add liquidity function, which has parameters, obviously, yeah? Asset A, asset B, and amount of liquidity you want to provide. So asset A, asset B determines which pool you want to add liquidity to, and then amount. Then you calculate how much liquidity, because now let's say it's an X5K pool, so I have two assets. So you determine a pool, you calculate how much liquidity of asset B the user should provide, and you resolve the transaction, right? Added liquidity. But you might not ask the question, what if I invert the assets, right? So what if user specify asset B and asset A then, right? So there might be some path which takes, and it receives incorrect number of shares, for example. Then insufficient validation, right? So you don't validate the shares of the user, for example, right? And so on. There is a nice list of, curated list of hacks, DeFi hacks, which I can show you. Here. Here. So this is a list of hacks, and all you can see here that this is the root cause, which was this is the project and the root cause of this problem, right? So we can see that a lot of this, like incorrect calculation, insufficient validation, access control, and so on. But the good thing is here of this that you can open like the detail, and you can see where was the problem in the code, right? So you can go through that after you implement your AMM and see if this can apply to your implementation as well. Many of it might not, because this is probably some smart contract. Not a lot of things are here from Substrate, but some of them, you know, something gives you an idea what can go wrong. So I want to mention just one, like, very famous hack, very easy to do, you know, and something we also have in our Basilisk implementation, something similar. I will show you later. That was that the AMM osmosis implemented the AMM, and then somebody discovered that if you add liquidity and immediately withdraw, you will receive, I don't know how many percent it was, I think around 50% more than you should have, right? And it was just keep repeating the process, and the pool was drained. I don't know how much they drank at the end, but it was quite a lot. So the conclusion would be, like, you have your spec, implemented according to the spec as accurately as possible. And the important thing is that choose your audit company carefully, right? Imagine, example. Our implementation in XYK in Basilis went through the audit. Nothing was found, but there was a problem, right? We had a similar problem what Osmosis had, right? That there was a possibility to receive more from the pool that you should have. To be said, it was well before the launch, so it was discovered, and I will show you how we discovered it. So something you can also try with your AMMs, the testing strategy we tried and discovered that there was a problem. All right, so yeah, so that would be the brief summary of AMMs, what it is, and what do we need to know to actually start implementing the palette, right, of AMM. So we have different types of AMM, so let's implement one. I decided to show you how to implement XYK, this constant product, because it's easy to understand. But as you will see, that using that approach, you can easily implement the other types, right? And like I said, I will focus on the things which might not be obvious at the beginning, right? Which will surprise, not surprise, yeah, it might surprise you when it comes to implementation. So there are questions that you start with, right? So you have AMM, so what do we need to store, right? Every pallet, each pallet has some storage, doesn't have to have, but you need to probably store something, like information about the pool, maybe about the reserves of the pool, like how much is in the pool at the moment, but you know, there is things to think about. So then you start having questions like, how do we represent the pool, right? Do we have a pool ID, or do we don't need a pool ID, you know? Next question is like, okay, we know that we need fees, right? So do we want a fee for the trades, right? Obviously we want the fee for the trades. Then do we need a withdrawal fee, right? In XYK probably you don't need, but for example, you implement an AMM which allows single asset LPing, right? That means that you allow users to deposit only one asset, right? In XYK, user has to deposit both assets, but you might find a way how can people deposit only one asset. So when then it comes to withdrawal, you also allow to withdraw another asset, right? So what that would mean, right? I deposit asset A, I get some shares, and I withdraw and specify I want asset B, right? So without the fee, it would be essentially a trade, right? So you might want to think about that as well, right? Then interface, right? So you designing your palette, so what interface do we need? Like, okay, we need to create a pool, then we need to add liquidity, remove liquidity, and then we need to, obviously, the most important part, which is the swaps or trades, sells and buys. So, and then when you think about all other AMMs, right, they will have the same interface, because you don't need anything else, right? So, and then you start thinking about input parameters, right? For create pool, what do we need, right? We need list of assets, which goes to the pool. We need probably some initial liquidity, right? Price, initial price, maybe. For add liquidity, same, like we need to determine which pool we are adding asset to. For remove liquidity, again, we need a pool. Like we need to know which pool it is, how much shares the user wants to withdraw. And for the trades, yeah, we need to know the pairs, right? I want asset B for asset A, how much? Maybe some limits like slippage to control the slippage. But if you think about it, in XYK, then you want to implement stable swap, you will find out that the interface will be the same, right? Or very similar. So you can take one approach and apply it to the implementing of the another one. So before you start also creating your AMMs, you might also think about the safety. About some safety mechanisms, like do I need a kill switch? Right? What does it mean? Imagine you have a pool running on your chain, everything is good, happy, everybody's earning, and then one of the assets becomes toxic, right? You don't want it anymore, right? But you have this pool running and you don't have even no way to stop it, right? So you should also think about like, how can we stop it, right? Do we want to freeze a pool? So how can we do that, right? Because, it's not easy. Or if we have, for example, multi-asset pool, like we have in Omni pool, we have many assets, right? So we cannot stop the Omni pool, right? Or we don't want to stop the Omni. So we need to find a way, how can we freeze only one asset, right? Or maybe you want asset only to be, the people can only withdraw the asset. You don't want any more liquidity of the asset, but you want able to get rid of it and you want the people to able to remove it. So you can find a way how can you only stop the certain operations, right? You can also think about some limits here, right, before you start. So limits, I mean, for example, minimum trade amount, minimum amount the people can provide, right, when they want to add liquidity to the pool, and then or maximums, right? Or you can also think about how much liquidity can be traded in one swap, right? Some ratio, for example, 1/3 of the pool can be only traded in one transaction. For example, Omni pool is currently researching a safety mechanism where we consider to take some liquidity offline when we detect some huge price movement, right? Or huge liquidity movement. So we are thinking about like automatically take some liquidity offline, right? So that can be one thing, right? It might not be easy to do in other AMM tools, but Omnipool allows us to do that. So for this workshop, I prepared like repository, right? It's in this. It's over here, right? I also added some tags. So there is a tag like step 0, step 1, step 2, and each step is basically we start step 0 in empty pallet. Step 1, implementation of create pool, which we will just start doing shortly. Then step 2, implementation of liquidity provisioning and withdrawal, and so on. So you can basically follow along. Let's say we won't be writing the code, but you can make your changes if you like, right? So everybody got it? So basically, this repository here, we have the pallet AMM, and inside you can see all the text here, right? Step 1, initial, blah, blah, blah. So you can check out whichever step you want to look at, and then maybe even compare within the text to see what's the difference. And then there is the math, then I will talk about shortly. It's basically divided, right? The implementation of the mathematical model is here, and the implementation of the pallet itself is over there. Okay, so we have already some ideas how can we start. So let's start with the first thing we need to do, right? So we want to have AMM. First thing you want to do is to be able to create pool. What do we need for this, right? So first question I would ask is permissionless or permissioned, right? Because this is something you won't think about, like somebody comes to you, I want to implement AMM. Okay, we can do that, you started implementing, and then permissionless or permission? What does it mean? we are in this decentralized world where we want everything to be as permissionless as possible. So there is no central entities which decides things. So we want to allow people to do it without you deciding, right? So do we want our XYK to be permissionless or permissioned, right? So this comes with some, both approaches comes with the problems and good points and bad points, right? Permissionless, you have to think about, do I allow people to create any pool, right? So then, do I allow people to be able to create same assets pool? You don't want. Probably you want only each pair should have only one pool, right? But then, you know, we will talk about like how to represent shares. You know, so then you need to think about like where do I get the share token, right? Share asset ID, right? So and then you start implementing your create pool, and then you come to the realization. Okay, so now Alice wants to provide liquidity. Okay, cool. Alice, give me your tokens, and you say, where should I put them, right? So how can we come up with a pool account, right? Because you don't want an account to be owned by somebody, right? So you might think, okay, I will add a parameter to the create pool, which also gives me the account where it should be moved, right? The liquidity should be moved. But then what happens is that somebody will create the pool at the account that you don't control, right? Does he own the account? Does he have the private key for the account? You don't want that, right? So you need to find a way how to create a pool account, right? But you want a pool account, a different pool account for each pool is created in your AMM. Then the initial liquidity, right? So I think the good approach is, if you allow anybody to create a pool, is to provide also initial liquidity, right? You don't want empty pools. Then fees, right? Do I want global fee applied to each pool, or I want a per pool fee, right? So that means, what do we need to know, right? So what do we need to store, and how do we represent the pool? So for the XYK, which we'll be now implementing, we will be looking at the code in a minute. So all we need to know is, we need to know which assets are in the pool. We need to know the share asset, right? Share asset ID. We need to know the account, and we need to know the reserves, the current balances of the pool. So the question marks here means that, do I need to store it in the storage of the pallet, right? These are the little things, like, do I need to store the pool balances somewhere, or can I figure it out, right? Because on blockchain, we want to store as little as possible. You know, storage is expensive, everything becomes more and more expensive when there is more stuff. So you need to find a way, how can you store as little as possible. So that's why I put this. Do I need to store the account which I just generated for this pool, or I can figure it out, right? We will see how can we do that. But for sure, we need to know which asset we have in the pool and what is the share asset, right? So for example, stable swap can be a little bit different. Like a stable swap can allow you to create multi-assets pool, right? So you can have more than 2 assets in the pool. This is XYK, we have only 2, right? There is some parameters of the stable swap, like amplification. You can also store the fee of the pool if you want different fees per pool, you know. And the same applies here. Do I need an account to store or a reserve, right? So for this is the step 1, right? And we just look at it. We will now look at it. How can we implement the create pool? Any questions so far? Is it clear? All right. So how many of you are familiar with Substrate? All right, cool. I won't be talking about what is the pallet, right? But I will talk about these things, right? So we have the create pool here, right? We know that the parameters will be like this. I want asset A, asset B, and I want the initial liquidity provided by whoever is creating the pool. I decided that my XYK pools will be permissionless, right? So I don't need the account, right? I don't need the share asset because it will be generated by this protocol. So as we said, it's permissionless, so anybody can do it, right? It must be signed account where we take the tokens from, right? We don't allow same asset to be created, right? The pool to be created with the same assets. So now you have a question, right? Now you have something to think about. Like when I determine the pool, how can I uniquely identify the pool? We know that we are not creating same assets, right? So, okay, we can determine the pool by the pair, right? By the pair. But what if user specify the revert, it reverts IB, right? So you can find a way how can you uniquely identify the pool. So I came up with this way, very easy, right? I sort the asset IDs descending or ascending. This is ascending. So I ordered the assets by the ID. The types you can decide if you want to be generic or not. For me, I just decided to be concrete types, which are specified here. Asset ID is U32, and the balance is not here, but balance is U28. But you can make it generic, and you can work with the generic type. If you want to represent your asset on your chain in a different way, for example, Akala doesn't have like the primitive type for asset; they have like an enum. So, but if you wanted to have like something like this, you would require the type would implement certain traits to be possible to be ordered, right? So this is our pair now. So we have the way how can we determine what is the pool, what's going to be. So now we check, right, if this exists. So what is this now, right? You may ask, right? So this is the storage, right? So we said we will be storing only information about what we need to know to identify the pool. So our storage for XYK is very simple, right? Because that's what we said. We don't need the account, we don't need the reserves, I believe. If you disagree with me, then raise your hand. We have the pools, right? And then we say, okay, the key will be our ordered pair. And the asset ID, this one, the value of this map is the share asset ID. We will come to that just right now, what it is. So this is all we need to know, right? Because when it comes to add liquidity, you can easily identify which pool it is. Yeah? You order the pair of the parameters, you look at this map and you say, oh, this pool exists, and I have the share asset ID. Okay. No, and now are the two difficult questions, in my opinion, when it comes to first realizing what you need to do, is where to take the pool account and share asset ID from, right? You want a pool account to be unique for each pool. So how can we find a way to easily come up with accounts which are unique for each pool, which don't have private keys, nobody can touch them, right? So, but still you don't know the chain, right? You don't know what chain is your AMM running in, right? So I like the way to delegate this functionality, to the runtime, right? So I think telling the runtime, give me the account ID for something, right? The something will be here. So we will configure our pallet to have this possibility to do, right? This part here. Right? So for this purpose, I created a simple trait, which looks like this, right? Which basically says that I want to create an account for these assets. Asset is generic, right? So it can be tuple, like we need, or if you, for example, wanted the same functionality for the stable slab implementation, where you have more than 2 assets, you can say I want implementation for a vector of several assets, right? And it's the responsibility of the runtime to have implementation of this trait and give you the unique pool ID, account ID, right? So basically here in our config we have this ability to create pool accounts. Right. So this is basically the concrete type we want the implementation for, and the result, the type which comes out of it will be the account. The account ID is the frame system account. You configure this in your runtime, right? In the runtime you have the frame system, and then you tell what type of the account ID this chain has, right? So, but you don't need to do that here. Yeah, you can implement this logic directly into your pallet, right? Because Substrate gives you something called pallet ID, which has the possibility to turn it into an account. There is a trait like into account. You can do that here as well. So you come up with a unique string, like for example, or string or whatever it is, which can then be hashed and create the pool account. You can do it here, but what this would mean is that you may, if you have different AMMs and you have the same way of creating assets, of creating accounts, you need to make sure that each AMMs would create the unique ones, right? Because if you created a pool between HDX and dot, for example, in XYK, and you have a stable sub where you create same pool, like HDX and dot, or not stable coins, but whatever, and you have the same implementation, they will essentially create the same account, right? So that's why I like to delegate this functionality to runtime to manage the uniqueness of the account. Okay, and so now the share asset ID, right? So when you provide liquidity to a pool, to determine who owns the liquidity, right? You can do it in different ways. We will also talk about it. But usually it's like you receive some shares. The shares are in the form of another asset, right? So how can I get the asset ID of the share token? Okay, now we can think about, okay, we can add an additional parameter to here, like this is the share asset ID, right? But then what that would cause is that whoever creates the pool would need also be able to register an asset, right? So it needs to know what is going to be my share asset ID. So now then, you as a maintainer of the chain, that depends on you. Do you allow anybody to register new assets? In that way, yeah, it should be possible. They register first the asset, then they create pool and specify the share asset ID. It's fine. But that means, but maybe you don't want this. You don't want to create random tokens on your chain, right? For example, in Basilix, we don't allow anybody to register asset. Only certain origins, like technical committee, can register an asset. So that means if you had this parameter here, it's no longer permissionless, right? You would need the creator of the pool first ask for the token, right? So, but you can come up with a way like that the protocol registers the token by itself, right? It registers new token, new asset, and uses it as share asset ID. So, and that's what we do here as well, right? We have the share asset ID, and it's done exactly the same way like we did for the create account, right? We have the asset registry, right? And it implements, and we require that it implements our trait, which is just create share asset for given generic assets, right? Again, you know, for our purpose here in the XYK, we will require it to be implemented for our tuple, ordered pair, and the output should be, again, the asset ID, because we want the same, and the error, right? So, and it's also now, again, the responsibility of the runtime to implement this or have some implementation of the registry itself. Okay, so, and now, okay, we have everything we need to represent the pool. We know how to store it, what to store it, how to generate the account, how to generate the share asset ID. So now we need to actually start calculating things, right? So we will look at the mathematics model a little bit later, but I like to have the mathematics model be part of another crate, another package. So imagine your research guy came up and implemented it in your somewhere else, and you're just using it, yeah? So we expose this the interface for you, calculate shares, simple stuff. So you just provide the initial state because this is the create pool, this is the initial state, so the current reserve will be 0, and the asset amount, because we decided that we want to calculate shares based on the token of asset, the first asset in the pool, and what's the last one? Yeah, it's total issuance, right, of the shares. It's 0 at the moment. So it gives you some shares which you should mint to an account. And now, okay, you have this, and now you hit another wall, right? Okay, I need to transfer stuff, right? So how can I do that? And I need to transfer and to mint stuff, right? So again, that's the responsibility of the runtime. Depends how the chain storing the assets, storing the balances, and handle the transfers. So yeah, so you delegate this functionality to the runtime, right? So, but you need certain things to be able to do, right? There are multiple ways you can do it, right? There is, for example, this ORML library, like Open Runtime Library, which has the multi-currency support. Or you can use the frame, this is all from the frame support library, from the Substrate, right? Which this is implementation of the fungible tokens. If you look at it, where it is, you know, it's in the support library tokens fungibles, right? So basically what we need is to be able to inspect an asset, right? So what we need from here is the total issuance and the balance. Right? So we say, okay, we need the implementation of this trait by something. We don't care what it is, but we need to be able to know what is the total issuance of an asset, because we will use this for the share asset ID, and we need to know the balance of an asset for this account. Right? This is what we need just from this trait. Okay, then we need to be able to mutate it, right? You need to burn and mint. Because when you add liquidity, you receive some shares, but they are minted, right? So we need again, right? Mint and burn. Easy. And then we need to transfer, right? Obviously, right? So simple stuff. We transfer from one asset to another. So that's what we require by our pallet to be able to do. So then you simply call this stuff. You transfer from the initial liquidity from whoever is creating the pool to the account. And then you mint the share asset. And then you store in your storage. You just said we need to store only the pair with the share asset ID. And then you mint, you fire some event, whatever. Okay, so that's the create pool, right? Now we have a create pool. Question, is it clear? You're happy with the way it is presented? Cool. So now, okay, we have a create pool, so now we need liquidity. We need somehow to add liquidity to the pool. Do we need to know anything about liquidity provider, right? Do we need to store anything about it? I don't think so. We don't, right? Now, how to check who provided liquidity? Like we said, we already said it. The answer is that we use shares, we use share asset. But can you think of any other way how can you represent the position in a liquidity pool? Omnipool uses that new approach, that approach. NFT, right? Instead of giving shares to whoever's providing liquidity, you give him an NFT, right? So Omnipool uses this. You get an NFT when you provide liquidity to Omnipool, which then tells you who owns the NFT owns the shares of the Omnipool, and there is some little details embedded inside the NFT, which tells how much shares this position has, right? But we already decided we will use shares because that's easier. And now, do we want some limits? Well, this is the safety mechanism I talked about. Min, max amounts, and the fees, like withdrawal fee I already mentioned. So this is the step 2. Now we look at how to implement the add liquidity. So this is obviously permissionless. Anybody can can provide liquidity to the pool. We decided that to identify the pool, we have the ordered pair, right? So the parameters of this is asset A, asset B, amount A, and the max limit of asset B. Because you require a liquidity provider in your implementation to provide both assets to the pool. So, but he specified only, I want to provide this amount of A, and you calculate the amount of B and the limit, like how much maximum amount of B can be provided based on the current state of the pool. The stuff is the same. We get the share asset ID. Also, this approach also gives us the possibility to tell that the pool exists or not, right? If it's in the map we have in the storage, then it exists, and if not, we can just return not found. It doesn't exist. The pool for this pair doesn't exist. Then we have the pool account, right? That's what we said. We don't need to store it, right? Because it's deterministic, right? So every time you call this is maybe not the best name because it doesn't create the account, it just constructs it. So it's deterministic. So every time you call it, it will give you the same result. So you can use that to get the pool anytime you need it. You know. Then, like we also asked the question, do we need to store the reserves or not in our storage, right? Yeah, you can store the reserves in your storage and you can read it from there, or you can figure it out, right? Because you can just read the balance of the pool account of each asset. It will give you the current state of the pool. And then, like I said, we have the mathematical model somewhere else. So we just calculate the liquidity in of the other asset, and we check the limit. And you know, this is like the provisioning. So we also calculate the shares, same thing as it was before. And again, the same thing like was in the create pool, right? We transfer from whoever is providing liquidity to the pool account, and we mint into the amount of shares which was just calculated. All right, so that's our liquidity. Remove liquidity, withdrawing liquidity is always the tricky part, but the approach is the same, right? You get your share asset, you get your pool account, you get your reserve, you get your share issuance, and then you have this liquidity out, which is the implementation of the mathematical model. But in this case, it returns two values, right? Because you need to return both assets to the liquidity provider. So you say, I want to withdraw this. This is not the best name because this should be share amount, right? And the share issuance. It calculates, does the magic, calculates how much you should receive. And again, right? Instead of burning, you will just do the transfer and then burn. And if you then want, you can also, if there is nothing left, you can destroy the pool, right? You don't have to, but you don't want to really have empty pools, I believe. So you can remove the pair and pool no longer exists. Can be created again, maybe. So that's our step 2. And trading, So this is the swaps, right? Again, we have the same, like how to identify a pool. We already decided we had the ordered asset pair to identify the pool. We can think about some limits, like I mentioned during the safety mechanism speech, that you can implement some limits there, trade limits, mixed amount limits, and fees. And now, okay, fees. Fees are also the tricky part. So let's talk about, so we have the XYK and we have two implementations of the swap, right? We have the sell and we have the buy. You can have one like called swap, but then it's not really clear what you are trying to do. That I like to separate it into sell and buy. Sell means that I want asset in, I want asset out. No, I want to sell asset in and get asset out, and I want to sell this amount, right? And the limit controls the slippage, right? So you can specify how much, no, mid-limit, the minimum we want to receive from the pool, right? So again, the same approach, right? As if we order the pair, we check if the pool exists, we get the account, we get the reserves, then, now we call calculate out giving in. So we are giving something to the pool and we want something out, right? So our calling implemented this in the second package. We will look at that shortly. And this gives you, based on the current state of the pool and the amount you want to trade in, it gives you how much you get out of the pool, right? But this doesn't include the fee. Could be part of it, but it's not here. But we calculate the fee here, right? So we have the fee set as a constant in the pallet. You can do it per fee, per pool, but that means you have to store it, right? We decided to do it for global fee for each pool will be the same. So fee can be, can vary, can be very small. So you want some fixed type, right? And you calculate the amount of fee from the AMMs out. Now there is the question you might be facing is like, to which amount I want to apply the fee to, right? Amount in or amount out, right? So given this interface, I would expect that the amount in won't change, right? So I want to sell 100 of asset A, I want to get something out of it. Just 100, I don't want less, I don't want more, right? I want to sell amount in. And the opposite applies to buy, right? I want 100, I don't want more, I don't want less, right? So in this case, we apply the fee to the amount, right? Which is calculated to be out of the pool. We apply the fee, right? So, and now we also, so we get the fee from the amount out, we subtract it. It could be done in one. So, but now it's two. And we get the amount less, the amount out which you receive from the pool will be less by the fee, right? We check if it's the limits you want, and then we transfer the assets. We transfer in, like into the pool, from the whoever is trading to the pool, and from the pool to the whoever is trading, right? So you don't need to store anything. You don't need to update of the state of your pool after the trade. Why? Because we decided that we don't store the reserves, the balances of the pool. So the state is automatically updated because it changes the balances of the pool. The same applies here, right? Same thing. We calculate the other way around, given in, given out, calculate me how much should I pay to the pool. We get a fee, we get the amount with fee. So there is a problem in this implementation. Can anybody spot it? I intentionally added a problem here because there is this little logic problems I talked about at the beginning. Maybe not even logic, like incorrect calculations, right? Like, which you might not realize when you dealing with amount in, amount out, fee in, fee out. So, but there is somewhere here is a problem. Yeah, it's the fee. This is the problem. It should be added, right? Which is not very obvious at the beginning, right? These little nuances you might see, right? You might not even realize, and might look okay in your test, because you write your test with certain numbers and everything looks fine, right? But actually what you are doing here, you are giving the trader more than it should have, right? Because you might not, you need to understand here that we are specifying how much I want from the pool, right? So this won't change, right? I want 100 of asset out, right? So I have to pay something with asset in. So, okay, we calculate here how much should I pay for my 100 in asset in, right? So then I calculate the fee, and then then we subtract it. This is incorrect. Then we subtracted this. So I paid less, right? I paid less of amount of asset in, right? Instead of I should pay more, right? So these things you can easily find if you implement good testing strategy, right? So you have this. We will see if you get to it because it's quite late. Anyway, so this was so here the correct should be add. All right, let's quickly jump to the most important part, and then that's the math, right? So your mathematical model, right? You came up with a new unique AMM. Your research guide implemented everything, came up with the implementation, the spec. It gives you everything you need to know how to implement this. So you start implementing, right? So here there are a lot of things, because now the implementation of pallet, like I said at the very beginning, is not that hard, right? It's basically repeating a lot of things, and just transferring, moving. But the most important part were in these functions here, right? That's where the magic happens, right? Of your AMM. So here, I like to separate these things, right? I like to have the math implemented in a separate module and have the pallet by itself, right? What this gives us is this easy testing and easy verification, right? You can just test the math. Is it correct? You can do invariance testing, property-based testing just on the math itself, right? And do you think there is another way? There is another good way why we want to separate it is that you can easily, because it doesn't depend on Substrate, doesn't need, well, maybe some of it, but you can easily compile it into Wasm, right? And have the same mathematical calculations used in the front end. That's what we do in Omnipool and Basilisk. We have implemented the math in the separate package, compile it into Wasm, and it's used on the front end, right? So you don't need to, because when you have the front end, you want to be able to show to the user that how much they will get, if they do the trade, without actually touching the runtime, touching the chain. You want to display, okay, if I provide liquidity of this, how much shares I get, right? So you don't need to implement the math again in the front end, but you can use the Wasm, and you can just call the same implementation. So whenever something changes, you just recompile everything, build everything, and you don't need to be worried about that the math is correct on the chain and math is correct on the front end. Another important thing is the fixed types, right? You are working in integer space here, right? So we have all balances stored as U128, right? So we are doing integer math, right? But to represent price, you need some fixed type. here you have to think about like how much precision do I need, right? So Substrate gives you this fixed U28, right? The internal representation is U128, and it uses 64 bits for the integer part and 64 bits for the fraction. Yeah. So, but you have to ask, is it enough for me, right? Maybe I need something else. I need more precision, right? I don't have a lot of before the comma and after in the fraction. I want more precision. That would depend, for example, if you have various decimals, right? You have tokens with various decimals. For example, our native token, or most of the token in Kusama or Polkadot have 12-digit decimals, but you can then an asset which is less, and then the precision might not be enough, right? So because you see that if you look at here, you have only this maximum. This is the maximum you can get, right? But you don't really care. I think, you want the price, right? Price is just some rational between the reserves, right? So it will be, so you might need more, right? So there are multiple ways you can get it. There are like fixed crates in Rust that will give you some variable precisions. So, but this is good enough for what you want to do, but something to think about. So the calculations, right, must be as accurate as possible, right? So now we can have a look at the math implementations, right? So I have the implementation of the XYK, right? So, for example, calculate out given in. This is used in the buy with sell, like calculate how much or the other way. How much should I, calculate how much asset out instead of for asset in, right? The calculation is very simple, right? But you can see that here, somewhere, we do the multiplication, right? So if you use just the balance type, like we said, the U28, this might easily overflow, right? So you won't get, they must easily overflow, but if you divide, it might come back to the type and fit in the type, right? So you need to think about that. I can really first do the multiplication, or I can divide first, because you won't need this higher precision type if you just revert this operation, maybe, right? You can just do the division first and multiplication first. But here is the problem, right? You are in the integer space. So imagine asset, I will give you an example. You have A divided by C times B, right? A is 10, C is denominator. C is 3, and B is 5. So if you first do the division, you get 10 divided by 3 is what? It's 3, right? Integer division. Times 5 is 15, right? But what if I just revert this operation? 10 times 5 is 50, divided by 3, 16, right? So you can see the difference, what it can make if you just revert the operation, right? So we need to realize that what is good for me, right? What is good for the pool? Should I always multiply first or division? I have the rule that I always do the multiplication first, because then you can avoid like multiplying the error. If there is an error in your division, and then you use it in the calculations, subsequent calculations, you can just multiply the error, and the rounding error can become huge, right? So I would just recommend, like, if you have calculation, like a lot of divisions, like think about how can you make it in a way that you minimize the rounding error, all right? But now we have the problem. If we multiply the first, we may not fit into this balance type, which is unsigned 128-bit integer, right? So we need to use the higher, right? So we need to convert first to something higher. So in this case, you can use 256. Should be big enough to do the calculations, and then convert it back to the price. Of course, it will be less performant because you have to do conversions. Depends how this is represented, how this is implemented. But what can you do, right? You want to be precise as much as possible, right? In some cases, you can just do the math without converting, but rounding, right? Always remember rounds in the favor of the pool, right? So imagine you are calculating the buy. Like, I want to buy 100, something has to be given to the pool, which is calculated, right? So if you do the integer division, you might end up with 16 point, like normal division, you would be 16.5, right? But if you do just the integer division, you get 16, right? So if you're calculating the amount you should receive to the pool, you are essentially getting less than you should have. You should get 16.5, but you're getting 16. So in that case, which we see here, is somewhere, you simply can just add 1, right? Because you know that even if you do the precise, like you get 16, right, after the division, well, I can get 1 more, User doesn't care one more, it's always in the favor of the pool, right? But you need to also think about that, don't apply the same rounding to amount out, right? Because if you apply the same to amount out that you're giving out of the pool, you don't want. So you want the division to be, the integer division that rounds down, right? So, and now, very important thing is like be aware what rounds up and what rounds down. Because I can give you a simple example, very simple, which surprised us, was Substrate has this fixed type we just seen, right? And it has a function called check mode in, right? Which can show you here. I don't know where it is now. Anyway, what was it? So I will show you then the calculations later, right? So there was a Substrate version 16, which now this is checked. It has a function called checked from rational, right? So it basically takes the two values and it constructs the fixed type, like checked from rational, right? So Substrate version 16, which we see here, this is the old one, right? You give this result, you can get this, right? But this, our pallet AMM, this is our pallet, uses the new version of the Substrate, and it will actually give you a different result, right? Not that much different, but it will be different, right? You see, at the end, right? So, and this won't be mentioned in the notes anywhere, right? That something was changed, that it always now rounds down instead of rounds out, right? Or this was not actually down or out; it was based on the on the fractional part. But now it always rounds down. So this is something you also integrate into your test, like, okay, to make sure that everything is as I expect it to be. Because it can change and you might not even notice, and suddenly you're giving, someone is draining your pool, right? All right, so now brief touch of testing. Like I mentioned at the beginning, we had a problem with the share calculations in our XYK implementation in Basilisk. I can show you what happened where this is what happened before, right? This was the unpatched version, right? The case was very similar to the osmosis hack, right? Where you could add liquidity and immediately withdraw it, right? This is Bob asset, and what I did in each step of this, I simply added liquidity and immediately withdraw it, right? Nothing else was done between the steps. right? And we can see that he received the same, right? This was the initial initial balance of asset, but he keeps receiving more and more, right? Just repeating this, right? And we see that the pool asset, the asset B in the pool keeps going down. Right? We are draining the pool, right? It might not be very exploitable because the transaction B might this offset a little bit, so it gets very expensive for somebody to drain it. But it's something doesn't look nice, right? So so this was what was happening, right? And with our fixed version, it looked a little bit different, right? How is his name? Bob. Bob kept again adding and removing liquidity, but he was less and less, right? Because that's what we had, this rounding stuff, right? So he keeps adding and removing, but instead of receiving the same amount what he got, what he provided, he's receiving less, right? Less and less. So it's not worth it for him to keep doing this. And you see that the pool asset is just increasing. That's what you want, right? You don't want just people draining your pool just because you did something incorrectly, some calculations that are incorrectly, and even doesn't look like a lot, right? It's a bad scenario you want to do. But now the question is, how did we detect it? Because like I said, it went through the audit, but it didn't find the problem, right? They say everything is fine, right? So I had a talk with Colin, right, our research guy, like each AMM has these properties, right? This invariant which should hold, right? So you have this constant like x times y should equal some constant. This should be this should hold basically before and after of any operations you do on your pool, right? So they said we can come up with a testing strategy. How can we just test our pool against as many as valid states as possible, right? So this is called, as you may know, if you are into testing, like property-based testing, right? You generate a lot of valid states, right? You generate valid state of the pool, you generate some random amounts you want to trade, if you want to test the cell, for example, and you run through this, right? And there is a certain invariant which must hold, right? So if you look at this, we have the add liquidity. Rust has multiple crates where you can do property-based testing. The one we use is called prop test, right? So you can define your strategy. Strategies here is like generate like valid asset reserve, valid state of asset in the pool, generate some, this is for asset A, for asset B, generate some valid amount which can be traded into the pool or added liquidity to the pool, and then just generate some correct issuance, right? Because you need to calculate shares, right? So basically then, like I said, if you have this separated, you can easily test this, right? And then there is your, somewhere here, is the following must hold, right? So if you take the old state, right, and the new state, and compare these two, it should hold, right? So this applies to the shares actually. So this was the problem we just seen here. This was the problem with calculations of shares, because Colin told me that this should hold, right? So then I was implementing this, and I said this will never hold if in our case when it was done wrong, because we didn't consider this in our calculations of shares. That was the problem we had. How they didn't find it, we found it fortunately before the launch. It was good. So, and then you just make sure that it, this hold, right? What he tells you is must hold, right? And then also the states, right? We have this, we are testing here in this property test, we test the buying variance. So we test the trading in against the liquidity pool. We generate the valid state, it must be valid state of the pool, right? And the amount we want to trade in. We calculate in and out, and then we take the original, the initial asset state generated here, the new asset state, and the property, the invariant must hold, and you're giving it some tolerance, right? Because there will be some tolerance which you are happy with, right? So when the invariant here, for XY cable, something like this, right? You take this is a new state, right? You do some square root. This is the mad magic. Can talk to him then. And then the new state and the new invariant must always be greater than the older one. That means if this was not true here, what would it mean? You mean that you are leaking some value from the pool, right? Somebody is draining your pool if the old state is less than the new state. And also then the invariant calculated here must be as close to 1 as possible. Yeah, there's a talk about integration testing, obviously, like I said, we configured our pallet to rely on other implementations, right? So we want to make sure that it works together with your AMM. Like if you, for example, we added the registry, so we wanted the runtime to be able to register assets. So if you do integration testing, then and briefly touch on benchmarking, which I don't think we have a lot of time, is that how much? All right, cool. That's enough. Like Gavin said during his talk, benchmarking is hard, right? Benchmarkers give you an idea how much your extrinsic cost, right? What's the weight of the call of the create pool stuff, right? And here it can be quite tricky to come up with the worst scenarios. Might not be in the XYK pool we just said, we just implemented, but it might be tricky in implementation of something where you use something more complex, right? For example, this is the implementation of the stable swap, right? In stable swap, you calculate this parameter D, right? And this is done like we see here somewhere in the explanation, right? In some very complicated way, right? So here in this, what is it? You do some iterations, right? And you do some iterations, you know, until the value here converge in some way, right? Also here, for example, back to the rounding issues, you know, we actually had to add 2 here, right? I'm just seeing, right? So if it converges, you can jump out, you can stop the iterations, and you are fine, right? So now, when it comes to benchmarking, they tell you that you have to find the worst case scenario, right? So you have some limits, right? Like how many iterations you do the max, right? I have implemented a way you can just do this like generically, you can specify, but usually it's around 255, right? Or 64 or some number, right? Which you have to test like what is good enough for you. But 255, let's say it's 255, right? So when you will be testing this, you will see that you will not reach more than 5 usually, with some valid normal state of the pool, right? But it's not the worst case, right? There might be a case which you didn't find, which actually can go to all 255 iterations, right? So you need to think about how can I force this to be the maximum iterations I specified for the benchmark only, right? So we see here that I found a solution, I think quite nice. No, it's the best, but for the benchmark purposes, I don't want this. I don't want to jump out, right? I want to force this iteration to go through all of it, even if it has already converged. So when you compile your node for the benchmark purposes, you give it this feature, right? So and if you give it this feature, it will run for the benchmark, so you will see that it will force it to be the maximum iterations you specify and you allow to be, right? So you benchmark actually the worst case, right? Even if you do converge in 5 iterations. So yeah, I think we are there. Questions?
Hello? Oh, okay. Hi. Is there a way that we can expose the calculation in versus out?
Sorry.
Oh, is that better? Okay. Is
Because
there a
I'm
way
behind.
to expose the in versus out to an external caller? Because when you are trying to integrate a front end to a Substrate AMM, it can be really annoying because you have to kind of duplicate your logic in the front end.
Yeah.
Because how come it's different between a Substrate AMM versus a Uni V2 pool or a curve?
But what do you want to expose?
I would want to be able to see how much I would get from the swap without doing
Yeah,
the swap.
because that's what I talked about, yeah? We had this math separated, and from Rust you can easily generate the WASM you can use directly in the front end, right? So you can take this, and you can expose the interface to your math in the WASM, which can be used by the front end, right? So we do this. So basically here, we have this math in our math package, right? So if we look at the dependencies here, we depend on our implementation of the math for all the pools we have, right? And then you create the interface here, which will be the WASM interface you want, right? So using this approach, for example, this is the XYK, right? So we have calculator given in, we want to generate some, bind it to some WASM, and you just call what you implemented in the Rust there, right? From this, you can build the WASM, right? So, and then this can be easily used by JavaScript because this will actually, can show you what it will generate. And if you go here, we go to XYK, web. You see it generate the WASM, but also JavaScript interface. And if you look out given in, it implemented this out given in the JavaScript, and it calls the WASM implementation, right? So, like I said, with this approach, you don't need to reinvent your math in your front end, right? You generate this is automatically generated, and you see here the WASM build from our math is just called here, right?
So it seems like somebody doing a very large trade would get a discount over somebody doing like their trades in smaller amounts. Is that a desired property, or is there more complicated math?
Yeah, you should think about what you want to allow, right? Like I said, you should also think about the limits. For example, the safety. You don't want large trades, right? Maybe you want, maybe you don't, but if you do a large trade, obviously you pay your fee with one fee and you get more, right? Obviously, with the smaller trades, you pay the same fee. But yeah, that's true. But if you take out a lot of liquidity from the pool, it might not be good for you as a liquidity protocol. So you might want to also implement some limits, right? We have the limit in XYK in our implementation bus list that only 1/3 of current state of the pool can be done in one trade, right? So if there is 100 of asset A, you cannot buy them more than 33, right? In one trade. So that will prevent this, for example.
Thank you.
So my question is, why do you make it with your own pallet instead of building the same thing with ink smart contracts, for example?
Can you repeat? Why do you?
Why do you making your own pallet for that instead of building the same stuff with smart contracts?
Why do you build your own pallet? So I don't know anything about ink, so I can exactly explain that. But if you rely on other things built by other developers, you want to make sure it's correct. So I believe that doing it, using what you can, but implementing the most important part by yourself is better, right? Because then you need to make sure that the thing that you are using is audited, if you want to be audited, right? And it was audited in a good way. So you need to do research on their part as well. But if you are doing, yeah, I agree with you. You should reuse as much as possible. But I think this AMM is complicated. It's very important, and if you get it wrong, you have a problem. So I think that in this case, you are dealing with a lot of liquidity, a lot of users, liquidity projects, money. So it's better to do it yourself correctly and get audited in the way you want. Right? But I agree, right? So
So you use the search statements, right? And you use it together with tests to ensure, actually not ensure, but you find flaws in your implementation. Do you know of any tools or crates that you can use to actually do formal verification? Because it seems like a problem that you actually want to solve with like infinite precision formal verification. Something like no panic, but for
yeah, I don't know any about that, but yeah, I don't know. I would have to do the research. Yeah, but yeah, so you should find good strategies to test also the formal verification, but I cannot answer it. Sorry.